Hi everyone, this video is going to cover a quick introduction to related rates and then cover some of our introductory related rates problems. So if you could turn to page 19 in your packets, we're going to do a little bit of stuff on here and then we're going to turn to the related rates day one notes. So we're going to talk through these two examples in class to really help you see why related rates are so important and where they're actually used in the real world. But the big idea here is that sometimes there are multiple variables in a situation that are all changing with respect to time. So we're going to actually jump down here though and talk about these two examples really quick. So this you should recognize as the area of a circle. If we talked about the area of a circle increasing with respect to time, that would be a related rates problem because the area is changing with respect to time and so is the radius. So they're related rates because they're related. Get it? I know I'm hilarious. It's fine. So we're going to, every time we take the derivative with respect to time, we have to make sure we use implicit differentiation because it's with respect to time. So we're not taking the derivative of the area with respect to the radius, we're taking the derivative of the area with respect to time. So that's going to be dA dt. And that means over here, when we take the derivative of r, we're going to need a dr dt because the radius changes with respect to time also. So the pi should just hang out, and we're going to take the derivative of r squared, which is going to be 2r, and then we need our dr dt. We need that chain rule, that implicit differentiation, since we're taking the derivative with respect to time. So we can just clean that up a little bit. So dA dt is really 2 pi r dr dt. So the derivative, the rate at which the area is changing with respect to time is equal to 2 times pi times r times the rate at which the radius is changing with respect to time. So we're going to do a very similar idea over here. Any variable that we see over here, we're going to need to use some implicit differentiation, some chain rule, in order to show that we're taking the derivative with respect to time. So this is going to end up being 2d dd dt equals 2x dx dt plus 2y dy dt. Every single variable gets its own derivative with respect to time. So we're going to look through some examples when we're back in class together. So you can go ahead and leave the rest of this blank. We're actually going to jump now to page 21. So if you could go to page 21 with me, that would be great. So it looks like this, solving related rates problems notes. This is really day one of your notes. So what is a related rates problem? It's usually a story problem, and in this story problem, multiple variables are all changing with respect to time. So we've got some strategies here for you. You could draw a picture, which really helps a lot when we're trying to figure out exactly what's going on. Then we're going to talk about listing the given information, and then we're going to determine or create an equation that will relate the variables you have in the problem. So we're going to go through an example and you'll kind of understand what that last bullet point means. So in question 1, it says assume the radius of a sphere is expanding at a rate of 12 inches per minute. So that's important. The radius of a sphere is expanding at a rate of 12 inches per minute. We're trying to find the rate at which the volume is changing. So there we go, there's our related rates already. We've got the radius changing at a certain rate, and we're trying to find the volume changing at a certain rate when the radius is 5 inches. So it's clear here that we're talking about a sphere. So let's go ahead and draw ourselves a picture of a sphere. And we know that a sphere has a radius r. Alright, so let's look at what we're talking about here. They told us that the radius is expanding at a rate of 12 inches per minute. Well, that's telling us the rate at which the radius is changing with respect to time. So that is dr dt. They're telling us dr dt is 12 inches per minute. they're asking us to find the rate at which the volume is changing with respect to time, which means they're asking us what is dv dt. And let's see, what's the last thing? Oh, the radius. They told us that at the specific point in time we're looking at, the radius is equal to 5 inches. So I need some type of formula that relates the radius of a circle, or a sphere, excuse me, with the volume of a sphere. So we got to think back a little bit to geometry, but hopefully you should remember that the volume of a sphere is 4/3 pi r cubed. And before you ask, yes, you are going to have to just know that. There's going to be a lot of formulas in this chapter with related rates that you're just going to have to know. So I would say write that down somewhere if you're not sure of it or if you don't remember it. Okay, well now I need to take the derivative with respect to time. So remember, we're going to need to use some implicit differentiation here. So the derivative of v with respect to time is really dv dt. Equals the 4/3 pi is just going to hang out because those are numbers. We're not going to take a derivative there. But we are going to take the derivative of r cubed. Again, remember your implicit. So this is going to be 3r squared and then dr dt, because that's that chain rule. So if I simplify this up a little bit and just make it look a little nicer, I get dv dt equals, these 3's cancel out and I get 4 pi r squared dr dt. So if we check out this formula, dv dt is actually what I'm looking for. The radius r was given to us, that's going to be 5, so we'll be able to plug that in. And then dr dt is that 12 inches per minute, which means we have everything we need in order to be able to answer the question now. So dv dt equals 4 pi times the radius squared, and we know the radius is 5, and then times the rate at which the radius is changing, which we know is 12. So now what we have to do is actually simplify that out. So dv dt is going to equal, let's see, 5 squared is 25, times 4 is 100, times 12 is going to give me 1200. So it's 1200 pi, and then I need my units. Since this is the rate at which the volume is changing, I know that this is going to be inches cubed per minute. Again, we're finding a rate, so you need to make sure that your units actually indicate that it's a rate, and the correct units. Since it's volume, it's inches cubed. Let's take a look at another one. So a crowd gathers around a movie star forming a circle. The radius of the crowd is increasing. So radius is increasing at a rate of 3 feet per second. How fast is the area taken up by the crowd increasing when the radius is equal to 15 feet? So this is very similar to the second one, but now we're talking about a circle. So here's my circle, and I know I've got this radius that we're talking about. So the radius is increasing at a rate of 3 feet per second, means that dr dt is equal to 3 feet per second. We're looking for how fast the area is increasing, so we're looking for dA dt, the rate at which the area is changing with respect to time. And we know at this particular instant that the radius is 15 feet. So we need a formula that relates the radius and the area of a circle. So hopefully we know area of a circle is pi r squared. And we're going to take the derivative with respect to time. So the derivative of the area with respect to time is dA dt equals, we're going to drop that 2, so we get 2 pi r and then dr dt. This is actually the one that we did over on page 19. But here's our implicit differentiation, and the pi just kind of tags along. So the 2 came from the r squared. Hopefully you're okay with that. I kind of jumped, sorry. But now we can see we've got it. So the rate at which the area is changing is equal to 2 pi times the radius, which is 15, times the rate at which the radius is changing, which is 3. So all I'm doing is plugging in the values that I was already given. So now I can simplify that. So I get that dA dt is equal to, let's see, 2 times 15 is 30, times 3 is 90, so I get 90 pi. And now I need my units. This is an area changing, so it's got to be squared. So feet squared per second. And there we go. There's my final answer. All right, we're going to do one that's a little bit harder. So if you guys could turn to page 22, and we're going to actually do number 4. So we're going to skip number 3 for right now. But I have a couple of things that I'd like you to change in this problem. So Sonia and Sana are in speedboats located at the center of Lake Down. At time t equals 0, Sonia begins to travel north at a speed of, cross off that 30 for me, and change that 30 to a 20 miles per hour. So Sonia travels north at 20 miles per hour. Sana travels east at a speed of, do me a favor and change that to 15 miles per hour. So traveling east at 15 miles per hour. At what rate is the distance between them increasing when t equals 12 minutes? So we're changing these values to make it a little bit nicer for us to kind of work with, because there's a lot of other stuff going on in this problem. I wanted nice numbers for us to do. So first thing we're going to do is try and draw a picture of what's going on here. So Sonia and Sana are both in the center of the lake. Sonia decides she's going to travel north. And Sana decides that she's going to travel east. So hopefully you guys are with me when I tell you that this is a right angle. Oops. And Sana's over here. And let's see, what else do we know? We're looking for the rate at which the distance between them is changing. So we're going to be looking for how quickly is this changing. Since both of these values are going to be changing, and actually all three of them, because the distance between them is changing also, they're changing the whole time, then we have to use some variables here. So Sonia's distance we're actually going to call x, since she's going east. Sonia we're going to call y, and I'm going to go ahead and call the hypotenuse here, I'm going to call that z. So let's write out what we've kind of got going on here. We know that Sonia, who's traveling north, has a speed of 20 miles per hour. So what that means is she's traveling 20 miles per hour. That then is dy dt. So we don't know what y is right now, but we do know that the rate at which y is changing is 20 miles per hour. And then Sana, who's traveling east, we don't know what x is right now, but we do know that she's traveling 15 miles per hour. So dx dt is equal to 15 miles per hour. Okay, what else? We're looking for dz dt, so we're looking for the rate at which this is changing. So dz dt, which is the distance between them, and this is the rate then that the distance between them is changing, that's what we're actually looking for. And we were given one other piece of information. We were told that we're looking for the rate that the distance between them is increasing when t equals 12 minutes. So one thing I'd like you to do really quickly, if we're talking about miles per hour over here, I don't want to talk about minutes here. So 12 minutes over 1, we're going to multiply that by 1 hour over 60 minutes, and we're going to convert that to hours instead. So the time is actually going to be 1/5 of an hour. So the time that we're looking at is 1/5 of an hour. And that's going to be important because we do need to know what these values actually are. So before we worry about that, let's think about a formula that actually relates all of these variables though. Since this is a right triangle, we should be able to look at this and know then that we can use Pythagorean theorem. So that means x squared plus y squared is going to equal z squared. Right? The sum of the legs squared, is going to equal the square of the hypotenuse. So if I want to take the derivative of this with respect to time, I need to remember my implicit differentiation since it's all with respect to time. So this is going to end up being 2x dx dt plus 2y dy dt equals 2z dz dt. Now if we look at this derivative that we just took, I've got dy, it's right here, it's 20 miles per hour. I've got dx right here, it's 15 miles per hour. I'm looking for dz dt, so that's great, but I still need x, y, and z. So that's where knowing that they've traveled for 1/5 of an hour is important. If I think about it, I know that I can figure out what those are because I know their speeds. So if this is my x, my y, and my z, I know that Sonia is traveling north at 20 miles per hour. And she's traveling for 1/5 of an hour. So if I multiply that, I know then that y is going to equal 4 miles. I didn't leave myself enough space there, sorry. In terms of x then, for Sana is traveling 15 miles per hour for 1/5 of an hour, which means x is going to equal 3 miles. So now if I think about my Pythagorean theorem again, x squared plus y squared equals z squared. Then I have 3 squared plus 4 squared equals z squared. So I get 9 plus 16, which is 25, is equal to z squared. I get that z is equal to 5. Oops, that should be in orange. So we can use some Pythagorean theorem here. If you know that you know your Pythagorean triples and you know 3, 4, 5, that's awesome too. But just in case it's not a triple, just remember you can fall back on Pythagorean theorem. But what that means is now I can use this formula and find the rate at which the distance between them is changing. So I'm going to have 2, and let's see, x is 3, and she had a rate of 15 miles per hour, plus 2y dy dt, and I know that y is 4 miles. She was traveling at a rate of 20 miles per hour, equals 2z dz dt. And we just found z to be 5 miles. So now all we have to do is simplify that out. So let's see, 2 times 3 is 6, times 15 is going to give me 90, plus, let's see, 40 times 4 is 160, equals 10 dz dt. 90 and 60 is going to give me 250, equals 10 dz dt, and I can just divide by 10. So I get dz dt is equal to 25 miles per hour. So the rate at which the distance between the two boats is changing is 25 miles per hour. So this one was a lot more involved. It had a lot more going on. We had to write our equation first and take the derivative, and then use our given information to find the distances on our triangle. And the reason all 3 of these had to stay as variables is because all 3 of them are changing. We're going to do some problems where some of the distances are actually constant, and so they won't be variables, they'll actually be numbers. So we'll do some of those examples in class. We'll kind of pull it all together. and make sure you guys are good before you get started on some practice. If you've got some questions, please make sure you wrote them down, and we will pull them all together in class. I'll answer anything you've got when I see you on Monday. Enjoy the rest of your weekend. Thanks for watching. Bye.